Hi students and welcome to another video lecture on logic design. In today's video, we will study the working of a universal shift register. By now, you should already know the following. A shift register that shifts data in one direction is called a unidirectional shift register. For example, the serial in serial out shift right register or the serial in serial out shift left register. On the other hand, a shift register that can shift data in both directions, either left or right, is called a bidirectional shift register. In comparison, a universal shift register will be able to shift data in both directions, that is left or right, and it will also have parallel inputs. So this is what a universal shift register looks like. I know it looks complicated, but let me break it down for you. The implementation of the universal shift register is done using multiplexers. In fact, it is made up of 4 multiplexers. The configuration of each multiplexer is 4:1. Each multiplexer will have 2 select lines, S1 and S0, and these select lines are common to all the 4 multiplexers. I have highlighted this common connection with bold red lines. Besides having 4 multiplexers, this register is made up of 4 D flip-flops. Each flip-flop is connected to an active low clear signal. This signal, when active, will force the outputs of the 4 flip-flops to go to 0. Each flip-flop is also connected to a clock signal. Always remember to put correct notations for positive or negative edge triggered flip-flops. The output of each flip-flop is named. Starting from the leftmost flip-flop, it is named as A4, A3, A2 and A1. The parallel output from this register is read also at A4, A3, A2 and A1. Parallel input is given at I4, I3, I2 and I11. So this is what we know so far about universal shift registers, that the circuit is made up of 4 multiplexers. The configuration of each multiplexer is 4:1 and each multiplexer will have 2 select lines, and these select lines are common to all the 4 multiplexers. I hope you remember the working of a multiplexer. For example, a 4:1 multiplexer will have 4 input lines A0, A1, A2 and A3 and 1 output line, that is Z. Also, to choose among these 4 input lines, there are 2 select lines S1 and S0. So, based on the values of S1 and S0, there will be a corresponding output of Z. The following truth table describes the working of a 4:1 multiplexer. When S1 and S0 is equal to 0, A0 input will appear at the output. When S1 is 0 and S0 is 1, A1 will appear at the output. When S1 is equal to 1 and S0 is equal to 0, then A2 will appear at the output. When S1 is equal to S0 is equal to 1, then A3 appears at the output. Now, with respect to the universal shift register, the select lines follow this truth table. When S1 is equal to S0 is equal to 0, then there is no change in the output of every flip-flop. But when S1 is equal to 0 and S0 is equal to 1, the data bits are shifted right through each flip-flop. When S1 is equal to 1 and S0 is equal to 0, data bits are shifted left through each flip-flop. And finally, when S1 is equal to S0 is equal to 1, then the data bits are moved into the register as parallel input. We will go through each connection in the diagram to understand this truth table properly. Let us look at the case when S1 is equal to S0 is equal to 0. So, since the select lines are common to all the multiplexers, we will have 0, 0 on these lines as well. So, since the select lines are both 0, D0 input will be activated on each multiplexer. And as per the truth table, when S1 is equal to S0 is equal to 0, there will be no change in the output of each flip-flop. So, let us take the first flip-flop to see how there is no change in the output. Notice the connection marked in red. A connection is made from the output of Q of the first flip-flop back to the D0 input of the first multiplexer. Also, the output from the multiplexer goes back as input to the first flip-flop. So, basically the flip-flop transfers each binary value it previously held back as input. So, basically there is no change in the output. Now, this connection is replicated for each of the other multiplexers as well. Let us look at the case when S1 is equal to 0 and S0 is equal to 1. So, since the select lines are common to all the multiplexers, we can have 0 and 1 on these lines as well. Since the select lines read 0, 1, the D1 input is activated on each multiplexer. And as per the truth table, when S1 is equal to 0 and S0 is equal to 1, the data bits will be shifted right through each flip-flop. So, let us take the first flip-flop to see how this shift occurs. For data to be shifted right, it has to be given at this point. So, the movement of data is like this. From D1 of the multiplexer to the output of the multiplexer. From the D input of the flip-flop to the output Q, and from Q back again as input to D1 of the second multiplexer. So, do you notice the path? The path shows that data is shifted right. There is a similar connection for each of the other multiplexers and flip-flops. Let us look at the case when S1 is equal to 1 and S0 is equal to 0. Please note that I have not changed it there down below. So, since the select lines are common to all the multiplexers, we have 1 and 0 on these lines as well. And since the select lines read 1, 0, D2 input is activated on each multiplexer. As per the truth table, when S1 is equal to 1 and S0 is equal to 0, the data bits will be shifted left through each flip-flop. So, let us take a look and see how this shift occurs. For data to be shifted left, data has to be given at this point. So, the movement of data is like this. From D2 of the rightmost multiplexer to the output of the multiplexer. From the input of the D flip-flop to the output Q, and from Q back again as input to D2 of the second multiplexer. So data is shifted left. There is a similar connection for each of the other multiplexers and flip-flops. Let us look at the case when S1 is equal to 1 and S0 is equal to 1. Again, I have not changed the values there down below, but assume that both S1 and S0 are both 1. So, since the select lines are common to all the multiplexers, we have 1 1 on these lines as well. So, since the select lines read 1 1, then the D3 input is activated on each multiplexer. And as per the truth table, when both these values are equal to 1, then the data bits are moved into the register in parallel form. So, let us take a look to see how this shift occurs. So, the movement of data is like this. In parallel form, through all the multiplexers, D3 input. The output of the multiplexers will move into the D input of each flip-flop, and finally this input will move out of the register as output of each flip-flop. Clearly, you can see parallel input and parallel output. That's all for now. Stay tuned to the classroom for more videos and learning material.